Can you guys see my screen? Yes, perhaps. Okay, cool. I can't see chat, by the way. I mean, I could if I opened it. Okay, cool. So, the 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 prominent topic was going to theory is what we should talk about. I just you guys, I want to talk this. And we know this, and it's very straightforward. We have rules about how to do this. But one thing you can ask is what kinds. One thing you ask is what kinds of functions are you able to reliably integrate? So, for example, okay, this is fairly straightforward. We can do this. But if I ask you, for instance, to try to compute the integral of this function, let's say in area 1 and in area would be right? Okay, great. So then maybe we integrate even more complicated things. For example, this function here has one place where the function is discontinuous, right? Oh, recording. Okay. Um, one place where the function is discontinuous. But what if, for example, I gave you and so forth? Recording is having trouble making up its mind. Um, could you do yeah. This is half times 1 plus 1/4 times 1/2 plus 1/8 1/4 dot dot dot, which is take a value of 1/2 divided by 1 minus 1/4, right? Which is 1/2 times 4/3. And so this total area is going to be 2/3, right? So this is all fairly straightforward. But what if I give you a really, really weird, bizarre pathological function? So for example, what if I try to give you a function that looks like, sorry, the screen share is janky. What if I try to give you a function that looks like, um, let's say 0 for all rational, or let's say it's 1 at all rational x, 0 at all irrational x. This is 0, this is 1. It's going to look like undefined. Go back to first definitions for integrating sequence of Riemann sums. Um, but maybe before we talk about that, I want to talk. about a little bit of set theory. Um, just, uh, oh my, yeah, I want to talk about a bit of set theory, just as sort of some introductory groundwork for a lot of the things that we're going to need to be able to discuss. So let us talk about some basic set theory. By the way, if I'm going too fast or too slow, or if you guys have any questions or anything like that, you can feel free to shout out or something, because I can't really see the chat too well. Okay. Um, so some basics of set theory. So I've already kind of mentioned sets a little bit, right? I've mentioned the set of points where x is rational or irrational. But the basic idea of set theory is this. A set is very simply a collection of, oops, of objects. So for example, I can define a set very simply as like um, a set of numbers, right? Like 2, 7, 8, 10.5. This is a set of four elements, right? Nice and straightforward. We can also, oh, we have someone else. Yes. Um, we can also define sets um, a little bit more exotically. Like we can define an infinite set, right? For example, we can define a set that is 0, 1, 2, 3, 4, 5, 6, 7, dot, 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 dot. And this is a set that we call, in fact, the natural numbers, right? Some people debate about whether or not 0 is in fact a natural number, but okay. Um, there's some infinite, very large number of elements in this set that we call the natural numbers. So we can define a set by enumerating the elements explicitly, right? Enumerating elements explicitly. We can also define a set based on a rule, right? We can say that an element A is in a set if it follows the rule, for instance, that let's say, so an A is in a set if and only if um, A is between 0 and, I don't know, 1, right? So this set would be the open interval from 0 to 1. And I say the open interval because 0 and 1 are not elements of A, right? By the way, I don't know how familiar you guys are with this notation, but this, I haven't written it very well here, but this symbol right here means element of. This symbol right here means not element of, right? Hopefully you've seen this, maybe, possibly. And this weird looking if here, if means if and only if. So that means this is true in both directions, right? If A is in A, then it's between 0 and 1. If A is between 0 and 1, then it is part of the set A. Okay, great. Um, so we can define sets like this. We can enumerate explicitly, or we can set aside some sort of rule that determines whether or not an element is in a set, right? Another thing we can do here is we can try to compare the sizes of sets. So if I give you a set that's like, I don't know, 0, 2, 4, 6, 9, right? And I give you another set that has 1, 3, 4, right? Call this set A, call this set B. And I ask, which is larger, A or B? This should be fairly straightforward, right? I think we can all guess which one is larger. You guys can put it in chat if you want, um, to show off your mathematical skills. But hopefully we are all able to see that A is larger than B, right? How can we see this? Well, the easy way to see it is that, well, A has 5 elements, B has 3 elements, We know from our arithmetic classes that 5 is greater than 3, and therefore we can say that the size of A is greater than the size of B. And I'm using these like type signs, these absolute value signs, just informally as a shorthand for like size. But really, we're going to want a more rigorous definition of size soon, right? Okay, great. That's one way of seeing why A is greater than B. There's another way to see why A is greater than B, which is to see that we can take an element of A and assign it to an element of B, and we can do that again, and we can do that again, right? So we're sort of establishing a mapping between elements of A and elements of B. And by doing so, we can see quite simply that the size of A is larger than the size of B because we have elements left over. Okay. Um, it seems like this is maybe not a better definition than the one we had previously, where we just directly assigned a number and then compared the numbers. But you'll see that this is going to be a better definition when we have sets that don't have an obvious number of elements, like let's say infinite sets. Um, okay, let's say we want to extend this definition and we want to figure out when two sets A and B have an equal size, right? Well, okay. Let's give ourselves two sets that we know have an equal size. Let's say 0, 1, 2, 3, and B is going to be, I don't know, 5, 7, 11, 13, whatever, right? And we want to know, are these two sets of equal size? Well, there's a simple test we can do, right? We can just see, okay, we assign each element of A to B, and we have no elements of A left over, right? We've used all the elements of A. Now we can try another thing. We can try to assign all the elements of B to A. Once again, we've used all the elements. We have no elements of B left over. So A is greater than or equal to B. B is greater than or equal to A. So we can see that A and B are of the same size. And I'm going to write that for now. Okay, great. Does this make sense for everyone so far? This is very straightforward, right? Okay, great. Now I'm going to write this a little more carefully, using a definition that we can then build off of. We're going to say that A and B are of the same size, and I'm going to use the word cardinality here. A and B are of the same cardinality if and only if there exists what I'm going to call a bijection between A and B. So what I mean by a bijection is a one-to-one mapping. Let me write that. A bijection is a one-to-one mapping between two sets. So if we have two sets A and B, we can try to map them into one another. If there's a one-to-one way to do this, we call it a bijection, and we say these sets have the same size in some very vague, loose definition of the word size. Sorry, there's some glare from the laptop. I mean, the lights. Okay, great. Now, this seems like a very obvious and useless definition for sets of finite size, but now I want to talk a bit about sets of infinite size. So let's take two sets and hypothesize whether or not they have the same the same size, and then use this test in order to determine it. I'm going to scroll so we have this much. Okay, cool. I'm going to take set A to be the natural numbers, right? So this is a set that contains, I like to start from 0. Some people like to start from 1. Okay, 0, 1, 2, 3, so on and so forth. And then we're going to have another set B, which I'm going to call all of the even numbers. And I can generate all the even numbers by multiplying the natural numbers by 2, right? So that they're all even. So that I get 0, 2, 4, 6, 8. And now we might ask, how does the size of A and B compare? How can we look at which one is bigger? Well, the naive sort of way to see this, um, yes, someone says A is equal to B, which is true, and we're going to see this in just a second. Um, but the naive sort of answer might be that these have exactly the same size. Sorry, that B is somehow smaller than A, because, well, all even numbers are in fact numbers, and there are still odd numbers left over. Therefore, A and B have the same size. But you actually have to be very careful with infinite sets. And it turns out that we're going to need to rely on this definition of the bijection we talked about, because it's very easy to actually come to incorrect conclusions if you try to do what are called surjective or injective mappings, which we won't have time to get into. You need to find a bijection and then see whether or not these two sets are equal. And so there's a very simple mapping, right? If we say that A is an element of A and B is an element of B, then every element in B is generated from an element in A by B equals 2A, right? 0 is mapped to 0, 1 is mapped to 2, 2 is mapped to 4, and so on and so forth. And so we can say A and B are in bijection, and so the natural numbers and the even natural numbers have the same cardinality. Same cardinality. Someone says that A is infinity. Sorry, by A here, I mean an element of A. So little a right here is, for example, it could be 0, it could be 1, it could be 2, it could be 3. These are all examples of A. And B would then be 0, 2, 4, 6. But you're right that the size of A is infinity, and the size of B is infinity. And so it's a little bit confusing to think about which one is larger. But okay, if we say that A and B must be equal because they're both infinity, then we can try comparing another set. Let's say now A is the naturals, right? Which we've just established. And B is the reals. Do we know what the real numbers are? So this is numbers like, um, you know, 0, 10, 2/3, pi, 0.42424341, 67.29, whatever, right? All the numbers you can feasibly think of, specifically all the numbers that you can write out with a decimal expansion, that may or may not be finite. Does this make sense to everyone? Okay, great. Um, Now, do people want to take a crack at which one is larger, the naturals or the reals? B is greater than A, great. Do you have an explanation why, maybe? After all, they're both infinity, right? Yes, there's a diagonal method, great. So let us go over. So the guy who first proved this was a guy named Georg Cantor. He was a mathematician in the, I want to say, 17th century, but I have to double check that. But he came up with what's called Cantor's diagonalization argument. Okay. So this is how Cantor argued that the reals have, oh, sorry, I need to charge my computer. How he argued that the reals have larger cardinality than the natural numbers. He said he did this using a proof by contradiction, right? So he said, let's say that we try to enumerate all of the natural numbers, right? Sorry, try to enumerate all of the real numbers, right? So we're going to index them using the natural numbers, and we're going to try and think of every real number, and we're going to write down a list, right? So we say um, 0.1 is our first real number, right? This is 0.1, great, 1/10. We'll write down another number. We'll write down pi, 3.1415926, blah, 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 blah. We'll write down another, by the way. Actually, what we're doing is we're considering all the reals over some interval, right? But okay, 3.1415926, blah, blah, blah. We'll also write down E, 2.71, so on and so forth. We'll also write down a random number I choose, which is 0.5692345. And we'll just keep writing down real numbers, right? Sure, we can do 5, but I don't. Do you remember the decimal expansion of 5? Because I don't. 0.6 something, something, something. Or there's a large one. But okay, yes, 1 point, you can use the large one too. 1.618, blah, blah, blah. You can do small phi, 0.618, blah, 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 whatever. We can keep writing down all sorts of real numbers. And what Cantor argued is that no matter how many real numbers you write in this way, all the way up till infinity, you will still be missing one more. How do we construct the one that we're missing? Well, it's simple. We say, let's use the first digit of the first natural number, and the second digit of the second natural number, the third digit of the third natural number, the fourth digit of the fourth natural number, and so on and so forth like this. This is why it's called the diagonal argument, right? Because you take the diagonal. Okay, great. Let's do this. And in our mystery number spot, let's put some number that's different than the one we chose. So the first digit of the first real number is 0. So let's choose, I don't know, 1. Then in pi, we have 3.14, right? So we'll put a 2 there. Now we have 2.71, so we'll put another 2 there. Now we have 0.569, so we'll put, I don't know, a 0 there. And we'll keep doing this forever. We can guarantee that this number here, the infinity plus 1 number that we've chosen, is not the same as any of the infinity numbers we've enumerated already. Why? Because it has at least one digit that differs from every single number, right? 1 differs from 0, 2 differs from 1, etc. It differs in every single position. Therefore, it's not equal to any of the natural numbers. Therefore, we can say that, ooh, we have another person. Therefore, we can say that it is impossible to generate a bijection between the real numbers and the natural numbers. Now, it's important to say what we're not saying is the weaker statement, which is that we can generate a surjection or an injection, right? We can write down a mapping and there will be stuff left over. Because if that were a strong enough statement, then we could say, well, between the evens and the naturals, we can just write down, 0, 1, 2, 3, 4, or rather, yeah. And we can try to fill in 0, 2, 4 by mapping uh, A to B. And oh, look, we have holes. We have stuff left over. We can't just say this, right? We have to say, not only is this not a bijection, but it's impossible to generate any bijection between the reals and the naturals. And that's how we say that the reals have a larger cardinality than the naturals. Does this make sense for everyone? Because this is a very counterintuitive concept, right? The naturals are infinitely large. The evens are the same size. They're also infinitely large. But the reals are infinitely large, and they're larger infinitely large than the naturals. Does this make sense, Rob? Okay, great. Um, there is a statement that there is nothing with cardinality between the reals and the naturals. So there is no set. There is no set. Oops, not. No set, I'll call it X, such that it has cardinality between the reals and the naturals. So such that naturals X is less than. This statement is called the continuum hypothesis. Um, and the reason it's called a hypothesis and not like the continuum theorem or something is somewhat subtle, but it has to do with the idea that this is not necessarily true. and it's not necessarily false. And in fact, it is impossible to prove slash disprove this statement, um, which is quite a curious thing. It's a result of something called Gödel's incompleteness theorem, but this is part of a class of statements that are undecidable in formal math. Um, and so, if you're interested in this, you can study Gödel's theorem, which are part of a branch of math called computability theory, which is very foundational to set theory. But okay, whatever. We have the naturals, we have the reals, they have different cardinalities. The reals has larger cardinality, and there's nothing in between them. Because of this set of facts, we like to use a certain terminology for this. We like to say that the naturals have countable cardinality. Ooh, we have another person. The naturals have countable cardinality because we can simply count them, right? We can go one, then two, then three. And in theory, if we keep going forever and ever, we'll reach the end, the end. Um, the reals, we say, have uncountable cardinality. Why is this true? Because you can't count them, right? You can try to count them in the way we did above. You can try to have some some special ordering. You can try to, come up with some function that takes the naturals to the reals, and it turns out this is impossible. There's absolutely no way to count the reals. There's no way to assign them indices that are of countable cardinality. So we say that reals have uncountable cardinality. Impossible to count. Impossible to enumerate a meaningful order to. Okay, great. Um, so this is a really interesting fact, and a very foundational idea in set theory. Um, and it's also going to come in somewhat handy. So I think we should probably go back to talk about integration then, if you remember our previous discussion, um, and talk a little bit more about putting integration on rigorous footing, because this is really the heart of where measure theory begins. Okay, so we were discussing earlier what kinds of functions are integrable, right? What kinds of functions it's meaningful to assign an integral to. So we decided functions like this are fine, right? We just take their integral. We decided functions like this, which have a single discontinuity, are also fine because you just split them up. And we've decided that functions that have some weird behavior like this, right, are very questionable. We're not sure whether or not they're integrable or not. Okay, great. Um, you might recall that I gave this example of this function that keeps getting divided in half, right? So up until 1/2, up until 3/4, up until 7/8, and so on, that this function has area 2/3. Um, does anyone want to take a guess at what property in particular makes this function integral? Why is this integrable? Because it has an infinite number of discontinuities, right? It's discontinuous here, discontinuous here, discontinuous here, and it'll be discontinuous at an infinite number of points. But what is special about the it's a geometric sequence, this is true. And so you're right that we can assign an integral to each of these, and then we can just sum over all of these integrals. There's a geometric pattern, this is true. But does it matter that there's a geometric pattern? Like, if I instead gave you a function that looked like this, and then at some other point, I don't know, this is 1/2, and then I chose a point, I don't know. Um, okay, let's keep it 3/4, right? I made it like this. But then I went wonky and I made it, I don't know, zero point 0.6. And then I went to 7/8 or something like this, right? Sorry, zero point 0.6 is not, I don't know, 0.76. If I did this, this function would still be integrable, right? Because you still just assign an integral to each of these little pieces, and then you sum over the integrals, right? So what is it that's special about the set of discontinuities? It's related to something we just discussed. It's countable, exactly. The set of discontinuities is countable. Great. And so if the set of discontinuities is countable, then we can split our function up into a countable number of regions where it is continuous, right? If we have um, n discontinuities, well, okay, n isn't right because it might be countably infinite. Um, but yes, we split this up into regions where it's continuous, and then we sum over each of those regions. Okay, great. So we've now established that countable number of discontinuities implies that a function is integrable. Is the inverse true, do you think? Um, uncountable number of discontinuities, non-integrable. You think this is true? Okay, great. Um, it's a curious question. I shouldn't put a check mark there. How would we go about proving or disproving this statement? Maybe. Yeah, it's certainly not obvious whether or not the inverse is true. Um, whether or not uncountable number of discontinuities implies that something isn't integrable. Um, uh, it's an argument. Yes, it's true. It's true. Um, I'm trying to think of a good pathological example. Um, okay, suppose you have a function. By the way, just a piece of historical interest, if you're curious. Um, it's not an unsolved Riemann hypothesis. I know the answer, um, and nobody has given me a Fields medal. But if you're curious, by the way, this function here is called. I thought I should mention it. Is called Dirichlet's function. Um, it's a rather famous example from this mathematician named Dirichlet. Um, uh, uh, and it might be of interest in thinking about this function to realize that the set of points where it is discontinuous is rational. So it's discontinuous at rational points. I don't know if you guys are familiar with this notation Q, but it just means rational, so you can write it as a fraction P over Q. Do we know what the cardinality of the rationals is? Um, if I ask you that. Um, there's a zero chance of a number being rational. Yes, this is true, although it is a somewhat misleading statement, and it's the reason why we have measure theory, because things that have zero chance still happen, right? This is somewhat tangent to the discussion, but it's important to measure theory. If I have a square here, right, and let's say this is a dartboard, um, the chance of hitting any individual point P is zero, right? Probability of P is zero. But obviously, we still hit some point. And so this is why measure theory is so useful, because it lets us define these zeros a little bit more precisely. Um, but someone says there's infinitely more irrational numbers than rational. Yes, precisely. Um, and because well, okay, if we believe the continuum hypothesis, this means that the rationals have the same cardinality as, well, okay, this doesn't actually necessarily mean this, but it is true that the rationals have the same cardinality as the naturals. So the rationals are countable. And then, if we believe the continuum hypothesis, then it is true that the irrational numbers have the same cardinality as the real numbers. Great. Um, so this is an interesting fact. So that means what I call Dirichlet's function, right? Dirichlet's function, which is f of x equals 0, sorry, equals 1 for x rational and 0 for x irrational, which looks again like this strange pockmarked thing. Um, has discontinuities at every rational number, and so it has countable discontinuities. Okay, great. Um, this is an interesting fact, and it might let us see that, well, in fact, this function is integrable, right? According to at least this claim that we've made up here. And its integral would then be 0. The area under this thing would be 0, because we simply break it into places where it is continuous, which is only over irrational intervals, and so the area is 0. Um, which is quite an interesting fact, right? Okay. Um, yes, this is true. Okay, great. Um, I want to talk a little bit about, well, first of all, I want to uh, come to this interesting conclusion here, which is that an uncountable number of discontinuities might be non-integrable or not. I don't know how much. Is this supposed to be 1 hour long? Um, okay, I don't know if I have enough time to go super into depth, but I do think it's worth discussing briefly. I want to take a brief diversion back to set theory to talk about a famous example of a set called the Cantor set. I don't know if any of you have heard of the Cantor set before. Um, but the Cantor set is a set that's constructed as follows, okay? So we take the real number line, right? And we select the points 0 to 1. This is fairly straightforward, right? Um, and now we're going to call this set, I don't know, C0, okay? Now we're going to take our next set and we are going to take the points of C0, which is one interval, and we're going to cut out the middle third. So that leaves us from 0 to 1/3 and 2/3 to 1, right? This is 0 to 1/3 and 2/3 to 1. I'm going to call this set C1. Okay. Now what am I going to do? I'm going to do the exact same process again. We now have two intervals, and so I'm going to remove the middle third of every interval. So now we're going to have 0 to 1/9 and 2/9 to 1/3 and I can do math. 2/3 to blah 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 8/9 to 1. Okay. 0 to 1/9 union. Um someone said 1/2. I don't know exactly what they meant, but okay, 2/9 to 1/3 union 2/3 to 7/9 and 7/9 to 1. Right now we have four intervals, and we're going to call this C2. And we're going to keep going with this process, right? Every time I have a Cn plus 1, I'm going to cut out the middle third of every interval. So the way we write this like a little bit more rigorously is that Cn plus 1 is defined to be Cn scaled down by 1/3 plus 1/3 of Cn shifted over by 2. Um, so for example, we would take this interval and squish it down into 0, 1/3. And we take this whole interval and we move it over to 2 comma 3, and we shift it over by 1. We scale it down to 1/3 the size. And we do the same thing, right, to get from C1 to C2, which is that we take this whole interval here, we scale it down to this, take this whole interval and shift it, and then scale it down to this, right? So this is exactly the same process as just cutting out the middle third of every interval, right? And we're going to keep doing this process forever and ever and ever, forever and ever and ever. And the limit of this process is what we're going to call the Cantor set. So this right here is the Cantor set. Um, Written a little bit more rigorously, it's actually the intersection of all of these CNs. But hopefully this process makes sense to you. Okay, so now we have this strange interval that has this strange union of intervals. Yes, it's exactly like a Sierpinski fractal. In fact, if you do this in n dimensions, if you do this in 2 dimensions, you get what's called a Sierpinski carpet. Um, if you do it on a triangle, you might be familiar with the Sierpinski triangle, which is exactly the same idea. But yes, this is a fractal, and it's got this very, very intricate structure of the union of an infinite number of intervals. Okay, great. Here's a question for you. Um, is the Cantor set countable or uncountable? This is not obvious at all, for sure. Um, because we're short of time, I will tell you right now that the Cantor set is in fact countable. Sorry, uncountable. Um, the way you see this basically is that if you want to select any point inside the Cantor set, like let's say this point right here is in the Cantor set, what you do is you basically make an infinite number of choices. You say that okay, we're in this interval. Let's choose to go left to this interval. Then we'll choose to go right to this interval. Then maybe we'll choose to go left to some interval. And we'll keep making left or right choices until we arrive at some point in the Cantor set. Um, you make a countable number of choices, right? Because the Cantor set is the limit of a countable process. Um, but at each place you choose one of two things. And so the cardinality of the Cantor set is the cardinality of 2 to the natural number of choices, which is the power set of the natural numbers, if you're familiar with that. And this isn't something I established, but there's something called Cantor's theorem, which says that the power set of a set must have larger cardinality than the set itself. And so this must be an uncountable set. Does this make sense? I know I made a few leaps of logic here, but hopefully it's at least reasonable to see that the Cantor set should have um, larger cardinality than the natural numbers. Someone asked another question. You don't have to delete your chats, I'm happy to read them. Um, okay, so the Cantor set is uncountable. So now let's say we consider a function that is, I'm going to call this c of x, which is 1 if x is in the Cantor set, and 0 if x is not in the Cantor set, right? So once again, just like the Dirichlet function, right? This is like some modified Cantor Dirichlet function. It looks like this. There's like a carpet up here and a carpet down here. Um, and we want to know um, what is the area of this thing, or rather, is it even integral? Is it integrable? You might remember that we made this conjecture here earlier that some of you thought might be true, which is that an uncountable number of discontinuities implies non-integrability. Um, and this was our conjecture, right? And so one way of testing that is to test whether or not this Cantor function, this Dirichlet Cantor function, is integrable. Um, because it has an uncountable number of discontinuities, right? We've established that the set of points that's in the Cantor set is in fact uncountable. And so now we just want to know whether or not this function is integrable. Uh, the answer, spoiler alert, I don't think we have time to prove it, although it is an interesting proof. But the answer is that this function actually is integrable, and that the area of this function is also 0. And so it turns out that this criterion that we believed may or may not be true. Do I have a different color? Yes. This is in fact not the case. It is not the case that an uncountable number of discontinuities is sufficient to prove non-integrability. And so it is true that if something is countable, or if the number of discontinuities, I should say, is countable, if number of discontinuities is uncountable, sorry, is countable, then you have integrability. Um, but this is not an if and only if statement. This does not go both ways. Um, which is an interesting fact to know. So now let's say we do want an if and only if statement. We want some criteria to tell us whether or not a function is Riemann integrable. Um, if a countable or uncountable number of discontinuities is not the factor that matters, what is? Um, gonna make a little bit of a leap of logic now, since we're running short on time, and tell you the answer. The answer is the important criterion is not that the set of discontinuities is is countable. Does anyone have a guess? Like, what is important about the set of discontinuities? Non-integrable leads to uncountable. Yes, this is just the contrapositive, right? If countable leads to integrable, then non-integrable leads to uncountable. This is true. This is the contrapositive if we take the continuum hypothesis as given, uh, which most people do. Um, but what's a guess for what their criterion is? Um, there's a specific reason I chose the Cantor set specifically, and not some uncountable set, right? The Cantor set is a very interesting property. Um, the observation about they are predictable. It's true they're predictable, but lots of things are predictable. Um, the observation that it's like a Sierpinski fractal is quite astute. There's something special about it because of this. And the special fact is that the length of the Cantor set is zero. This is not difficult to see, right? Um, the length of the first iteration of the Cantor set, this has length 1, right? The next one has length 2/3. The next one has length 4/9. It's pretty easy to see that the nth iteration of the Cantor set, the nth iteration of the Cantor set will have length 2/3 to the n. So as you take the limit, you're going to get 0, right? So the Cantor set, yes, it's true. The chance of a random number being in the Cantor set is 0. But again, some measure theory will clarify this. Um, but yes, so the Cantor set gets smaller and smaller in length until it reaches length 0. And so the important criterion is that the set of discontinuities has length 0. I put this in quotes because length 0 is a little bit vague, and we're going to come up with a better term in a second. But really, what we want to say is not quite length 0. This isn't the word we want to use, but we want to say that it is measure 0. This is the big takeaway term. The area of the Sierpinski triangle is 0. Yes, the area of the Sierpinski triangle is 0. The area of the Sierpinski carpet is also 0. If you're not familiar with the Sierpinski carpet, it's like the triangle, but you do it with squares. Um, the area of the Sierpinski cube the volume of the Sierpinski cube is 0. And in fact, you might be seeing that length, area, volume, these are all manifestations of something more general that we call measure. So length is measure in one dimension, in Euclidean one dimension. Area is the well-defined measure in 2 dimensions. Volume is the well-defined measure in 3 dimensions. And so I've introduced the surface area of the Sierpinski cube. The surface area of the Sierpinski cube is actually infinite, um, but its volume is 0. So surface area is not quite, um, the surface area would not be the measure of the cube itself, but the surface area would be the measure of the shape that forms the boundary of the cube, um, which is in fact a 2 dimensional shape, right? Not a 3 dimensional shape. And so we have this idea called measure, which is a word I've just made up. Well, I mean, I haven't made it up, but it seems like I've made it up, which corresponds to somehow length in 1 dimension, area in 2 dimensions, and volume in three dimensions. Um, there's a lot of interesting reasons why we might want to consider these all kind of the same property measure. And there's a lot of reasons why we might want to define this idea of measure a little bit more rigorously than just, oh, it's like, how much stuff there is vaguely. Um, because it turns out that measure has some very strange properties. Um, if any of you are familiar with something called the Banach-Tarski paradox, by the way, I know we're almost out of time, but I'll might go a few minutes over. Um, if any of you are familiar with something called the Banach-Tarski paradox, it's this famous paradox where you take the unit ball in three dimensions. Um, you take the unit ball in three dimensions, and you split it up into, I believe you need at least five shapes, five like sub pieces of the ball. And they're not simple divisions. They're these very intricate, these very intricate uh, different shapes, and you take them apart and you put these shapes back together in such a way that um, you get two such balls. And this might seem like it's a violation of something like conservation of volume or something like this. Um, but the real answer to this is that well, measure theory is going to explain why this process actually is not a problem. It has to do with the fact that when you choose these five shapes to break up this ball into, they are what are called non-measurable sets. The set of points is non-measurable. Someone mentioned spatial plus temporal dimensions of space-time. Yes, and there's plenty of ways that people have tried to rigorize this idea. Um, but if you're curious, sort of the idea is that you attach like an imaginary number to stuff, and you get something that's called Minkowski space, um, or Minkowski space-time. This is going a little bit off topic. It doesn't have much to do with measure theory. Um, but the way that you define Minkowski space-time instead of normal space-time is you change the dimension of you, you you change the definition of distance from being instead of s squared is like x squared plus t squared. You have a definition that goes s squared equals x squared minus t squared. And this is how you differentiate between like the spatial dimensions and the temporal dimensions. But this doesn't have much to do with measure theory. Is the ratio of radii like cube root of 2 to 1? Not quite. The issue with the Banach-Tarski paradox, the reason why it's called, um, this is how it's spelled, by the way, if you're curious. I know it became very famous a few years ago because Vsauce made a video about it. The issue is that these all have the same radius, and so it seems like this should be impossible. Um, but anyways, okay. We're getting a little bit off topic. The idea that we want to talk about is measure, and I'm going to try to illustrate to you with a very simple example why it's important to actually think a little bit carefully about measure and length and make sure it's well defined. Um, and the big question to ask here is is measure even well defined for every set? Someone says no. Great. Do you think it's well defined? Is it well defined over? Is it well defined as a length, for instance? Like if I want a measure over the real number line, right? Is measure well defined? Well, okay. First of all, what are the properties we want of a measure? Um, there's really only like one big property that's important of a measure. So first of all, what is a measure, right? A measure is often written with the with the letter mu, right? This is the Greek word for measure. Sorry, Greek letter that symbolizes the sound like m. Um, if you've done any physics, it's used to like represent coefficient of friction and stuff. But anyways, the measure mu is a function that takes as its input some set, some domain, and it gives you a number from 0 to infinity. Note that I've included 0 and infinity. Um, this is because you can have a set of measure 0. This is the empty set. And you can have a set of measure infinity, right? The whole real line has measure infinity, we should hope. But anyways, a measure is a function mu that takes in some a and gives you a number from 0 to infinity, some scalar. And we want it to have really one important property, which is that it's additive. So that means that the measure of the union of some sets is equal to the sum of the measures of those sets. This is really the important axiom that defines measures. So for instance, like the measure of the set 0, 1, 2, 3 should be the measure of 0, 1 plus the measure of 2, 3. And this is in fact true, right? Because this is 2 and this is 1 and this is 1. So that makes sense, right? At least using our usual definition of measure on the real number line, which is just length. Okay, great. So the question is, this measure that we've invented of length, is it well defined or not? We might have some guesses as to whether or not it's well defined. Um, but let's see. We might want a measure that, for instance, well, okay, the properties of a measure that represents length that we would definitely want are, we want this measure if given an interval AB to spit out a we want to spit out the number b minus a, right? So if I ask for the measure of the set of points between 0 and 1, we want it to give me the length 1, right? If I want it to give me the measure of, I don't know, 1.5 to 3.5, it should give me the number 2, okay? So this is our first axiom of length as a measure. Our second axiom is that we would want, if we have some set of points, let's call it E, and we add a constant to all of them, right, C, we want this to be equal to the measure of E. In other words, we want our measure to be translationally invariant, right? If I give you the set of points 0, 1, I want the measure of this to be equal to the set of points from 4, 5, right? If I just shift over all my points, the measure shouldn't change. The length shouldn't change, as long as this is a rigid transformation. And the last property that we want is a property that the measure of the union of sets should be equal to the sum of the measure of those sets, right? This is just a property of all measures. We want measures to be additive. And then lastly, just sort of as a definition, we want this measure to be a function that takes in the domain of allowed sets of points, and I'll choose that in a second. I'll enumerate that better in a second. And we want it to return a number between 0 and infinity, inclusive. Infinity is an allowed value, right? And then lastly, what is this set A? Well, in fact, this set A is, and this might not be obvious, but I'll try to convince you in a second, is 2 to the reals, right? It is the power set of the real numbers. Why? Because it is the set of all sets of points in R1, right? Um, you can describe any set on the real number line as the power set of the reals, just by at every single real point establishing, is this point in the set or not? That's a 0 or a 1, right? So 0 or 1, 0 or 1. To every number on the real number line, you assign a 0 or a 1, and you get 2 to the R, or the power set of the reals, right? This can also be written as the power set of the reals. Okay, great. So this is what we want our measure to adhere to. Does this function exist? We wonder. Well, let's try to construct it. Or if we can't construct it, let's try to find a counterexample, right? Um, so for example, by the way, an example of a well-defined measure would be um, a well-defined measure over finite sets. Over finite sets is simply the counting measure, right? Like if A is, I don't know, 1, 3, 5, then the measure of A is 3, right? It's just the number of elements in your set. So this is one example of a well-defined measure. Is cardinality a well-defined measure, do you think? We define cardinality above, right? Um, the answer is that cardinality is not quite a measure, right? Because the cardinality of the numbers from 0 to 1 is is uncountable. Cardinality of the numbers from 1 to 2 is uncountable. But the cardinality of the numbers from 0 to 2 is the same uncountable. So cardinality is not a measure. Um, but okay, let's try to see if this length measure exists. I'm going to claim it doesn't exist. And I'm going to construct a counterexample uh, to the idea of a well-defined length. So here is my counterexample to a length measure. So I'm going to consider the points from 0 to 1, right? So this is the real number line. I'm going to consider all the points from 0 to 1. Okay, great. This has a simple measure of 1, right? We know that. Um, and what I'm going to do is I'm going to divide all of these points into what I call, let me scoot upwards a bit. I'm going to define all of these points, divide all of these points into what I call equivalence classes, okay? I'm going to divide them into what are called equivalence classes. And I'm going to say that two numbers, A and B, are equivalent if and only if A minus B is a rational number, right? So for example, 0 would be in the same equivalence class as 1, in the same equivalence class as 1/2, in the same equivalence class as every single rational number, right? 0, 1, 1/2, every rational number, P over Q. These are all in the same equivalence class. What else is in the same equivalence class? Well, um, let's say 1 over root 3. This is an irrational number, right? But it's in the same equivalence class as, let's say, 1 over root 3 plus 0.1, or 1 over root 3 plus 0.2, or 1 over root 3 plus any rational number, right? Okay. So we all agree that these different equivalent classes exist. And it's not difficult to show that they're all disjoint, right? Okay, great. Now I'm going to construct a set I call V. And it's named V. Does that mean root 3 is not the same one as... Yes. Um, 1 over root 3 is not equivalent to 1 over root 2. But rather 1 over root 2 generates its whole own set of equivalent numbers, right? 1 over root 2 plus 0.1, 1 over root 2 plus p over q, right? So if you add any rational number to a number, it'll stay within its equivalence class. This is clear to everyone. Okay, great. Now I'm going to construct a set that I'm going to call V. The reason I'm calling it V is because this set was originally discovered by this Italian mathematician named Vitali. So these are often called Vitali sets. Okay, take my Vitali set V, and I'm going to um, choose one point from each equivalence class, right? So one and only one point from each equivalence class, right? So I'm defining this set to choose one and only one point from each equivalence class. Um, and that means we know that basically the difference between any two elements of our Vitali set is uh, is always irrational, right? Does this make sense? Okay, great. Um, we also know the cardinality of the Vitali set. What is the cardinality of the Vitali set? It's countable, right? Because all of the equivalence classes differ from each other. Okay, great. So that means, trying to recall the rest of the proof. Yes, that means that the, first of all, the numbers 0, 1 are all contained within the union of all possible Vitali sets, right? And the union of all possible Vitali sets is, since we only shifted this over by 1, sorry, I think I have to introduce the shifting yet. Um, Give me a second to quickly reference my notes. I'm missing a step here. Um, the basic idea, oh yes, the basic idea is that you add a rational number between 0 and 1, right? You add a rational p over q between 0 and 1, or sorry, between -1 and 1, to each Vitali set. So now you have some collection of Vitali sets that is countable, right? And it is countable because you've added a rational number. All of these Vitali sets must be disjoint, right? It must be disjoint because points in the Vitali set differ by irrational numbers, and here we're adding a rational number to each Vitali set. Great. So now we're going to, we can enumerate this with some numbers like qk, right? These are the set of rationals that we're adding. Rationals are, let's say, p over q in 0, 1. And so we have some collection of Vitali sets, vk, which is v plus q sub k. And again, this is countable. Why? Because we can have some countable index k because there is countably many q sub k. So now what we know is that, firstly, 0, 1 is entirely contained within um, the union of our v sub k's, right? By the way, I used this notation earlier. I don't know how familiar it is to all of you, but hopefully you've seen unions like the one I used here. Union just means you're combining multiple sets, right? That may or may not be disjoint. So that to that. So now let's take our many Vitali sets. We'll take the union of them, and we can show that the interval 0, 1 must be contained within that collection of Vitali sets. This is not difficult to prove. The fact is that all numbers between 0 and 1 are either rational or differ from a rational number by an irrational number. Great. We also, however, know that the union of these Vitali sets is contained within -1 and 2, right? This is obvious because we took a number between -1 and 1 um, and added it to a number between 0 and 1. So of course, it can't get less than -1 and it can't get more than 2, right? Great. So we know this is true. And therefore, using the axioms of Vitali sets, we are going to, sorry, the axioms of measures, we're going to say that we're going to take the measure of this whole inequality. And that's going to give us the fact that, well, the measure of the interval 0 to 1 is less than or equal to the measure of the union of our Vitali sets. It's less than or equal to the measure on -1 to 2. This means, well, this is 1, right? This is 3. And this, using the axioms of measures, is the sum of the measures of each of the Vitali sets. And so we have this inequality right here. Does anybody see the issue by now? We have that the sum of countably many measures is within 1 and 3. But notice that all of these measures must be equal because we want our measures to be translationally symmetric, right? So they all have the same measure as the original Vitali set. So that means that 1 is less than or equal to the sum over countably many k's of this number, mu v, is less than or equal to 3. But if you take a number and you add it to itself an infinite number of times, it can only be zero or infinity. It can't be unbounded. Sorry, it can't be bounded, right? So therefore, we have a contradiction. And so the Vitali set V has no meaningful measure. I know I rushed through that proof a little bit, but does the gist make sense? Does at least the conclusion make sense? There is no function measure you can give to the real number line that satisfies all of those axioms because the Vitali set will not satisfy all of those axioms. Okay, great. That is the last point I wanted to get through. I know I've gone a bit over time. But this is the basics of measure theory. Measures are are these functions that take in some sets as their domain, some collection of sets as their domain, and spits out some number that roughly gives you sort of like a sense of the size of the set. And measures don't always behave as you would expect them to behave. Um, I should give a small confession that the proof that shows that this meaningful measure doesn't exist uses something called the axiom of choice, which the Banach-Tarski paradox also uses. I won't get too much into the axiom of choice, but if you're curious, um, you can Google it. It's an interesting axiom. Um, it's an interesting piece of logic that some people say causes more issues than it solves. But this goes back to the foundations of set theory and stuff, so you can look at that on your own time. Um, that's basically it. Did anyone have any questions? Or if not, then we can be done.